Hey guys, welcome back. This is Frank, and welcome to our IGCSE Co-Sci Physics revision videos. Our current unit is P4 Light and EM Spectrum. So, today I'd like to talk a little bit about lens diagrams. So, this is one of the most important, concepts and topics discussed in the entire unit, and it's really helpful to know and fully understand how lens diagrams work because it will not only help you on problems that require a lens diagram, but also on problems that doesn't quite require tell you to draw a lens diagram, but it will be still very useful to kind of draw it. And it's also useful for solving problems about where the image is located, even if they didn't give you a lens diagram, because you can draw one yourself and you can just see for yourself, and you don't need to really need to remember or memorize all of these. But anyway, uh, before we dive into how to draw lens diagrams, I'd like to first introduce you to five situations that we're going to discuss today. So the first one is when u is greater than 2f. So basically, this u means the distance between the object and the center of the lens, or the optical axis. And this f, as we've seen it before, is the focal length. So basically, what it's saying is that this object is placed, beyond twice the focal length, or as we can see from this diagram, this 2f is where it represents like twice the focal length, and this object is outside 2f, so it's beyond like that length. And this situation is when u equals 2f. This is when 2f is uh, less than u but greater, oh sorry, less than f, less than 2f but greater than f, so like between 2f and f. This is when u equals to f, and this is when u is less than f. So to begin with, I'd like to introduce some of the common ways. Well, actually, one common way to draw a lens diagram is, and I'll write over here, method. You draw two rays. Okay, so two rays, we have one ray that is, oh, and actually I should be more specific. So two rays that goes from top of object. Okay, so these two rays are gonna be, number one, parallel to principal axis. All right, so we know that light rays that goes parallel, that comes parallel to the principal axis, is gonna go through the focal point on the other side, or I should say principal focus. And another ray we should draw should go through center of lens. And we know that rays that goes through the center of the lens is gonna come out, well, the direction is not gonna change, so direction unchanged. All right, so basically we're using special rays here, one that is parallel and one that goes through the center, because we know these two are kind of special and we can expect where we're going to find them. And by using these two rays, we're going to find a point where they converge, because it's a converging lens, and we're going to find a point where these two rays converge, and that's going to be where our image is going to be. All right, because this comes out from the top of the object, then the converging point is also going to be the top of the object. So in this way, we're going to tell, we can tell if the image is upside down or right side up. All right, so moving into our first situation, we have u greater than 2f, so the image distance, the object distance is greater than twice the focal length. What we're gonna do here is, as discussed in our method, we're gonna first draw a light ray that is parallel to the lens, the principal axis. So let me just use this over here. It goes like this, and we know that it's gonna come out through the principal focus. Just gonna connect this over here, come out through the principal focus. Oops, might have put it up a bit more like that. All right, and sorry, and for this one, we know it's gonna go through the center of the lens, so it's gonna somewhere over here, like that. Cool. So let me just show the arrows real quick. So that goes from this way over here. All right. So as I've just said, we're gonna find a point where these converges. So let me find another color. Let me use this green. This is a point where these two lines, these two rays converges. So we know that because they both came out from like the top of the object, it's gonna be the top where the top of the object is on the image. So we know that the top of the image is going to be over here. So we know that it's gonna be upside down, and then uh, we can just because the base is on the principal axis, so we can just ignore the base. The base is still gonna be on the principal axis. So the top and the base, we connect them together, and oops, and I don't know why I can't do that. Like that, and then like that. All right. So as we can see, although not very clearly, but it's good enough, we can see that first of all, uh, the V is between f and 2f. We use V here to stand for the image distance, or the distance between the image and the center of the lens. So it's this distance right over here. I'll just label it out uh, on this one. So this distance is V, and as we just talked about, this distance is U. Okay, so we know that V is going to be between f and 2f, because that's what we see on the diagram. And you can see how like this ray diagrams are useful, because we can tell a lot of properties of this image. So we know that this is going to be diminished. So I'm just gonna write it down here. So diminished basically means that this image is smaller than the original. So if you take out a ruler and compare the the image, the diagram of the image and the diagram of the original object, is going to be smaller. So we also know that it's going to be inverted or upside down. All right, because the top of the object is down here. And the third one is a bit hard to tell on this diagram, but it's actually it's actually easy to tell. But you might not think about it in the first place, but if you do the actual experiment, you're gonna find out that you can project this image on the screen. So for images that we can project on the screen, that we can actually, well, we can't actually touch it, but like we can actually uh see it on the screen. It's called a real image, as we discussed in the last video, as opposed to virtual images, which are images that cannot be projected on the screen, and we're gonna soon see which images are virtual. But for this one, we know that it's going to be diminished, inverted, and real. All right, cool. So that's our first one, and our second one is actually exactly the same as what we did right over here. Basically, what we do is, as we always do, find first of all a ray that is parallel. So maybe like that. And oops, I think I've chosen the wrong color. It's this one, and I put it here. And then it's gonna go through the principal focus over here. And then another one is going to go through the center of the lens. So the center of the lens, like that. Oops, I think I missed it. Somewhere over here, I guess it's good enough for me. And I'm just gonna label it with arrows. This one's over here, and this one over here. And boom, we can see that similar to the one before, we also have a point where the image, the rays converges. So this is going to be the point where our image forms. And magically, we did our diagram very accurately. Well, as accurate as we could. So we can see that it is actually exactly on the 2f point. So we can say that the image distance is exactly 2f. All right. So we know that when the object distance, the distance of the object is 2f, the distance of the image is also going to be 2f. And let's try describing some of the properties of this image. So, well, it's maybe hard to tell on this diagram, but if you take out a ruler and measure it on your, if you draw it on paper, you're gonna see that this is going to be the same size as the original object. So this image is going to be the same as big or as small as the original object. So yeah, and another thing that is the same as the previous one is that it's inverted. We know that because it's upside down. The arrowhead now points down, and it's real because we can project it on the screen. All right. So when the object distance is 2f, we know that the image distance is also going to be 2f. It's same size, it's inverted, and it's real. All right. So moving on, when the object is between f and 2f, what we're gonna get is just get our ruler, draw a ray that's parallel, like, oops, like that, somewhere over here, and then we can start from over here, and then pass this through here. Oops, that was a bit too long. Maybe pass this till here, and we're gonna put it over here, and this one's going to go through the center of the lens. It's going to go all the way here. All right. So as you can see, very interestingly, I don't know if that's a word, interestingly, they converge somewhere over here. All right, so this is going to the point where they converge. And I think we just ran out of space, so I'm just gonna extend this axis a bit, if you don't mind. Because I can see that we're not. Okay, cool. This should be enough. So we see that the rays converges over here, so we know that our image is going to be over here. So let me just, oops. Yeah, and it's going to be go like that, or like that. Cool. So this is a point where the image is, and as we can tell very apparently, this is way beyond 2f. So we can very confidently say that v is greater than 2f in this case. And similar to that, we can see that this is actually much bigger. I think this one's very successful because we can see it like very apparently. This one's the image is much bigger, so we can say that it's not diminished, it's enlarged. Basically means it's bigger. It's inverted as before, and it's real. Cool. Moving on. This one's a bit tricky actually when the object distance is the same as the focal length. So basically what we're gonna do is same thing. Put over here. Put over here. Oh, sorry, wrong color. I'm gonna use this color. Put it down a bit. Maybe put it up a bit. Okay. Over here, and then go through the focal point. Okay. And we're gonna have another light ray that goes through the center of the length. So it's gonna be somewhere over here. Gotta be very accurate. And goes like that. Cool. And then we can draw the light rays. Draw the arrows. And oops, I think something is terribly wrong here because apparently I don't see these two lines converges anywhere. Uh, so what's the problem? Like, it it doesn't converge. Well, I mean, if it doesn't converge, then I guess you're just out of luck. There's no image. So we can say that these two light rays come out parallel to each other, so they're never gonna converge. So there's never gonna be an image formed because well they never converge. So we don't have to describe apparently the property of this image because there's no image. So we're just gonna silently move on and pretend nothing happened. And our final situation is when the object distance is less than the focal point, and this is the focal length. I mean, sorry. So this is also a very interesting one, because well, you'll see why in a second. We're just gonna start drawing as we usually do. So it's going to go through the center of the lens. So maybe somewhere over here, and then from here it goes to the focal point. I think that should be accurate. Put over here. And then another ray that goes through the center of the lens. So it goes like that. Oopsies. As you can see, again, these two rays don't converge. But there is something very oops, I think I missed the arrows. But there is something very interesting about this one because even though it doesn't converge like on the right side of the lens, it's gonna converge on the left side of the lens. So what we're gonna do is if we extend this a bit, so if we say extend it over here, and if we extend this one as well, so this one's gonna go from the center to and ta-da! We can see that this actually converges somewhere over here. So I'm just gonna put an arrow here and draw it down. Actually, you know what? I'm gonna use a dotted line. Okay, actually, I think I used the wrong color. So what we're gonna do is use the right color and draw a dotted line. This is a converging point, so this is gonna be where the head is. And as you can see, I used the dotted line because we extended this rays, right? So these rays aren't actually going backwards from the lens. It's just that we extended it. And the fun part is, because we extended it, it's not real light rays anymore. It's going to be virtual light rays. So basically, uh, what we have just found is a virtual image. But before we go into that, let's just quickly look at some properties of this image. So as we can see, it is enlarged. All right, so well, apparently this is much taller than this one, and we also know that this is upright, so it's not upside down anymore, and we know that this is virtual because you cannot project this on the screen. As I've just shown, you know, it's not real light rays. It's when we extend real light rays and they meet on the other side of the lens. So this image is going to be on the left side of the lens, as opposed to these ones. These ones are gonna form an image on the right side of the lens, and these images are gonna be real. So yeah. So to summarize, okay, actually, before we summarize, I would like to draw a quick diagram of what we've learned today. So, this is, well, if you can memorize this is gonna be really helpful. But if you can, don't worry about it. This one I created it myself, so I'm kind of proud of it. Well, actually not. But anyway, so let's say this is like the principal axis, right? And here we have 2f and f. So this is the focal length, and this is like twice the focal length. And let's draw some. Let's condense all of these into one single diagram. So we know that when the object is between, well, is greater than f basically. When the object image distance is, object distance is greater than f. So up until here, it's going to be real, first of all, and inverted. And on the right side of the lens, actually. On f, exactly, we don't have an image. And when it gets greater than f, so when it goes out between the axis and the focal point, it's going to be virtual and upright. And it's going to be on the left side of the lens, or you better say like on the same side of the object. And on 2f, exactly, we know that the size is going to be the same, so same size. But before that, it's going to be diminished. So let me just write this. From here to here, it's going to be diminished. And from here to here, it's going to be enlarged. So from 2f, and it goes on and it goes on, it's going to be enlarged. And another thing that I forgot to talk about in this one is that the application of this, the real life application of this, is actually magnifying glass. So this is how magnifying glass works. It is basically a lens with like a super long focal point, a super long focal length. Sorry, so that the object you put is going to be like within the focal length. So it's going to be in this situation where the image formed is going to be on the same side as the object, and it's going to be virtual, and it's going to be enlarged. So hence the name magnifying glass, because it magnifies. So yeah, just a fun fact that you could know. So it's you apply as magnifying glass, and we can also write over here. So this part is magnifying glass. Cool. So, to sum up, today we learned about how to draw ray diagrams, how ray diagrams work, and 5 different situations for convergent lenses drawing a ray diagram. We learned about real and virtual images, diminished, same size and large, inverted and upright. These are some of the properties of images. And we also learned that, how magnifying glass works. And this diagram, I think, is very important. Uh, Basically summarizes everything we did in this session. So, yep, note it down somewhere. And that's about it for today. And I hope to see you guys in the next video. Bye.